Hello again, this is James Camp from Lee College in Baytown, Texas, and these are my notes on Chapter 6 of Big C++ by K. Horstmann. This is part 1 of Chapter 6 where we'll deal with one-dimensional arrays. The chapter goals are to become familiar with using arrays and vectors to collect values, learn some common algorithms for processing them, and write functions that receive and return arrays and vectors. So, why would we want to use an array? There are several times that come up in programming where you're managing a list of data. Maybe you've got a list of grades that you're trying to process the statistics on, or you have a list of banking transactions that you're trying to sort through, or you have scientific measurements that you're trying to analyze. Or maybe you have more of a data-oriented program where you're keeping a list of email addresses that you're going to use to manage a mailing list. You can think of many more examples where you have more than just one or two pieces of data. Now, let's say you want to hold them all in memory while you do some operations on them. So far, we've dealt with multiple pieces of data by just reading them in and writing them right back out to the screen. But what if you want to sort them so that you're printing them in increasing or decreasing order? What if you want to search through this sorted list so that you can find something quickly in alphabetical or date order or something like that? What if you want to calculate statistics? You can total up and average numbers as they come in from the keyboard, but some more complicated statistics, like the standard deviation, require multiple passes through your data, so you've got to be able to keep them in memory. What if you have a list and you want to add, edit, or remove items from it? You have to have it in memory so that you can modify it. Again, you can think of probably many more examples of cases where you want to do some operations on memory. So far, all we've learned how to do in this class is create a lot of named variables. Grade 1, grade 2, grade 3, or Fred's email and Janie's email. This gets very cumbersome after a while if we're trying to keep up with a lot of values. Reading in grade 1, grade 2, grade 3. Well, what if we don't know how many grades there are? What if we have emails for just our few best friends, but then we meet somebody new? How do we add that to the list if we only have these named variables? So let's consider another motivation for being able to store lots of values in a single kind of indexed list variable, okay, an array. When you look at this set of numbers and I ask you which is the largest, as a human, you're able to kind of scan the whole list and the number 115 sort of pops out at you as looking larger than the others. If I asked you to find the smallest, it might be a little bit harder because you can't use the length of the number as an indicator, but you'd eventually circle in, well, there's 35, there's 32, there's 29, 29 smallest. Computers can't do that. They can only compare two numbers at a time. So what you would have to do before this chapter, before we get into arrays, is create one variable for each number, n1, n2, n3, all the way up to n10. Then you'd have to write a whole bunch of if-else statements, like if n2 is greater than n1, then you would compare n2 to n3. Else you'd compare n1 to n3, and so forth and so on until you'd compared all possible combinations of numbers and found the one that was largest. That's not convenient for a number of reasons. As we can see, even with 10 numbers, that approach gets very cumbersome. So really, the named variable approach only works for a small number of items. Second, you have to know exactly how many numbers you'll be working with when you write the program. If you want to find your highest grade out of all of your quiz grades in this class, you would have to know exactly how many quizzes you had taken so far, and you'd have to rewrite the program every time you add a new quiz. That isn't very convenient. And finally, there's no easy way to iterate through them all. You have to mention them all by name. which means that you have to do that complicated if else thing that I was talking about in the previous slide. What if we could chain a whole lot of items together in a single variable? Common English, we might call it a list variable. And in fact, in C#, there is a type of variable called a list, but in C++, list has a completely different meaning that you might get into in your Programming 3 course. But for now, we're going to call it a list, and we're going to say that the list items could hold any number of items, and you could iterate through them as items at index I. So the first item, the second item, the third item, the fourth item, all the way up to the 105th item if you want. In C++, we actually have two distinct ways to do that. The first, and the simplest from a computer science point of view, is the array. An array is simply a block of memory that is set aside with one variable naming a whole bunch of slots. So you can think of an array, as being a memory block that's much longer than what's necessary to hold a single variable. And so it contains 1, 2, 3, 4, 5, 6, 7, 8, in this case 9, has enough room to store 9 individual values. And so the array grades might point to this whole block, and then you can have grades at index 0, 1, 2, 3, index 0, index 1, index 2, and so forth, that lets you iterate programmatically through the whole list. There's also something called a vector. Now, vectors are made possible by the fact that C++ is an object-oriented language. Vectors are much more advanced computer science-wise than arrays, which actually, peculiarly enough, makes them easier to use. But because they're a more advanced object-oriented structure, we're going to discuss them last. We're going to discuss arrays first. Both will let you access any element as grades square bracket I, that's pronounced as grades at I, or grades index I, or grades subscript I. I like the at because it's easier to say. The vector adds an ability to adjust its own size and can tell you how many items it's holding at any given time, which makes vector far more versatile for most purposes than the array. Again, we'll get to vector later. You can easily visit each element in an array or a vector. You can check the value, you can update the value. You can, if we wanted to know the maximum, we would check this spot. We would check this spot and then this spot, and if this spot's bigger, we hold that one in memory, and then we check this spot, and if it's bigger, this spot, this spot. Every time we find a bigger value, we store that in memory as a value called largest, say, and we just have to iterate through the list once to find which value is largest. Much, much easier than all those ifs and elses we were talking about earlier. When the need when you need to work with a list of values, in most cases, the vector construct will be your best choice. By using a vector, you can conveniently manage collections of data. You don't have to worry about how big the block of memory they're being stored in is, or how many values you have in the vector, because it will automatically grow or shrink to any desired size. But vectors are both a bit more complicated computer science-wise, and they are specific to C++, whereas arrays are something that you'll find in just about every computer science language, certainly every C family language. So we're going to cover the vectors later. Arrays are what we call a low-level construct. It is, as I said before, just a block of memory with that holds, say, 10 or 100 items with a single variable name pointing to it. Because it's just a block of memory, it's less capable than a vector. It doesn't know how big it is. It doesn't know how many items have currently been stored in it. But it's much more efficient than a vector, because all you need to do is assign that block of memory, set aside that block of memory, and you can instantly jump to any spot in it and read from it, write to it, erase it, whatever you want to do. Most importantly, the array is compatible with standard C programs. And if you, like me, transfer to a four-year university that has a class in, say, Unix programming or low-level operating system programming, chances are they're going to teach you some operating system programming in the actual standard C language. So you will not have vectors. You will have to work with low-level arrays. In fact, you'll want to for an operating systems class, because the operating system is dealing directly with memory. It's not dealing with data structures that may move the memory around from time to time, which is something that vectors do. Okay, all that is to say, arrays are built into the C language and work almost the same way in all the C family languages: C, C++, C#, Java. So we're going to spend most of today talking about arrays. We're going to spend all of this lecture talking about arrays, and we're going to introduce vectors in the Part 2 lecture. I will note real quickly that in C# and Java, arrays work almost the same way, but they are defined slightly differently, so you'll have to look at your C# or Java language manual to check exactly how you define those. So whether you're using an array or a vector, you're storing a list of data. Okay. One thing that they both have in common is that the stored data has to all be of the same type. You can think of a sequence of data like the 10 numbers that we were trying to find the largest number earlier. Some of those look like integers, 32, 54. Others, like 67.5 and 44.5, are definitely floating point numbers. We can't store some of them as integers and some of them as doubles in one array. So what we have to do is promote all the integers to doubles and choose a single type that works for all the data in our array. So for this list of numbers, we would create an array of type double. And that array would be declared in a way that looks like this: double values, square brackets to tell the compiler that we're creating this as an array, and then to initialize that with the list of 10 numbers that we've been working with, we put those numbers in curly brackets separated by commas. Now, here's some basic array syntax. To define an un-initialized array of 5 integers, we go with int myArray. We put a numeral 5 inside the square brackets, and that tells the compiler to set aside 5 memory boxes, 5 integer-sized memory boxes for that matter, to use with the variable myArray. If we want to initialize an array of 4 names, we can put a 4 inside the square brackets to tell C++ to set aside 4 string-sized memory boxes, and then we can put the names of our friends in quotes because they're strings, in curly brackets to indicate that it's an array separated by commas. If you choose to initialize the list, you'll note that the number inside the square brackets is optional. C++, the compiler for C++ is smart enough to count how many objects you have here, 1, 2, 3, 4, 5, and say, okay, they obviously want a size 5 array, so it would set aside 5 double-sized memory boxes and then pre-fill them with those 5 numbers. Note that the array can be larger than the initialization list. This is something that gets done in standard C all the time. Again, if you ever take an operating system class, you'll have to deal with passing messages between 2 programs. And what they do is they'll set aside a buffer of, say, 256, or in this case 255 bytes of memory, and then it'll only fill that buffer with the number of spaces that are needed for that that message. So what happens to the rest of the buffer? Well, if you initialize part of an array, the remainder of the array gets filled up with zeros. So this array would have 5 letters, J-A-M-E-S, and then a whole bunch of zeros, 250 zeros after those letters. Okay, a side note that's not in your textbook but is really worth knowing here. A string is basically an array of type character. In standard C, there was no string type. Because strings, as they're defined in C++, are an object. They're a special kind of data structure that needs to know some information about itself. So strings are able to manage how many characters they have, and they're able to let you add to them and subtract from them and things like that. Those capabilities, object-oriented programming, was not built into standard C. It's still not built into standard C. That's one of the pluses in C++. So in standard C, you defined a large array of characters and then partially filled it. So you might set aside 128 characters for a username, knowing that most people are not going to create a 128 character username for themselves. And then you can read from the keyboard. The way you did that in standard C was using the scanf function. And you told it that you wanted to read a string and you wanted to store it in username. And let's say the person typed in the username jcamp. It would fill the first 5 characters of username with JCAMP, and then it would put a 0 after that to indicate that the string was done. You can actually still do this in C++. You can create a character array called username, and you can read it in from the keyboard using the cin and the input operator. This is the only kind of array you can do this with in C++. If you tried to do this with a bunch of numbers and read them in with cin greater than number array, you'd get probably a compile error. Okay, here are some quick syntax examples. Here's a size 10 array of integer. It's often done in programming. It's considered good style to define a constant that holds the size of your array and then use that constant to define the array, and then whenever you want to refer to how big the array is, you've got that constant hanging around in memory. And that's helpful because if you ever need to change the size of your array, let's say you find out that 10 is not enough numbers and you need 12, you can just go to wherever you define the constant size and change it once, and then everywhere else in the code, that's automatically fixed. Note that it won't work to make a non-constant integer size equals 10, numbers at size. This will not work because the compiler needs to know a constant size for the array at compile time, and this way it looks like you might change size at some point in the program, and that would affect the size of your array, and that's not legal. Another thing you definitely cannot do is read size in from the keyboard. How many numbers do you want? User enters 10, make an int that's size 10. Doesn't work that way. The compiler has to know the size of the array at compile time. Okay, so some terminology here. An array is made up of lots of numbers or characters or strings, as we've talked about. Each point in the array, each item that you store in the array is called an element. Okay. To access an array element, you use the notation values, or whatever your array name is, open square bracket, a number, close square bracket. The number I here is called the index of the array, or the index of the value. Okay. Now note that the first element in the array is at index 0, not index 1. Okay, not index 1. And the reason for this, again, is that if we imagine our array as a continuous chunk of memory boxes, so there's the memory box for our first integer, second integer, third integer, fourth integer, and it just kind of keeps going on. The name values actually points to the memory location of the very first box. And then the number inside the square brackets acts as what we call an offset. So if I had put 2 here, if I put values square bracket, that's supposed to be a square bracket, not a curvy bracket, values square bracket 2, that would tell C++ to jump forward 1, 2 spaces and look at the value in this memory box. Well, that happens to be the third memory box, but it's got index 2. So if you look at this array that I've defined here at the bottom of the screen, index 0 is the first number, index 1 is the second number, 2 is the third number, etc. This may be annoying. It's particularly difficult for first-time programmers to wrap their heads around, but most programming languages work this way, and so you're just going to have to get used to it. The index is 1 less than the number of the item in the list. Okay. So if we want to access the fifth element, 35, we would use values at 4. Okay. So if I hit C out, values at 4, end line, the output would be 35.0. If I wanted to get the sixth element in my array, I'd go to 1, 2, 3, 4, 5, 6. That's index 5. So I'd put values open bracket 5 close bracket, and that would give me my sixth element. Okay. Now that you know how to tell C++ which element you want, you can use array elements like any other variable. You can use assignments, max equals values at 6, you can use assignments in the other direction. Values at 7 equals 23.4. That replaces whatever's in the 8th box of values with the value 23.4. You can see out values. You can directly output them. You can also see in values. You can read whatever the user types at the keyboard into the first box at values or the 10th box at values. It doesn't have to be values at 0. You don't have to read them in an order. You could read them in random order if you wanted to, though it usually works better to read them in an order to make sure that you're using your array efficiently. Okay. An error. It is very common for beginning programmers, it's even common for some experienced programmers, to forget this rule about indexes being one off from the number of the item in the list. So if you're trying to say, well, I want to output the last item in a list of 10 values, you might write cout values at 10. That's error. 9 is the last valid index. Okay, what would the output be? We don't know. What this actually does is, remember our array is a box, a long chunk of memory boxes. So let's say this is box 9 here. So that's the end of our array. This would be another piece of memory. This might belong to another variable in your program. It might even belong to a different program entirely in older computers that didn't have memory protection. So choosing values at 10 would try to output whatever nonsense value is in that memory box. Like I said, it could be another variable from your program, or it could be just a random memory value that was left there by another program. Worse still would be trying to set that value. Values at 10 equals 33.3. That's going to try to write to this box, even though we may not have permission to write to that box. That might be outside our program's allowable memory, or it might be like I said, another variable that our program is using for something else. This can corrupt other data in your program and cause unpredictable results, or it can, if you're writing to memory that's outside the memory that your program has permission to write to, it can completely crash your program. Most of the time doing this will ultimately crash your program. There were in older computers an ability to just keep writing after you reach the end of your program's memory area, and you could really corrupt the entire computer. You could crash the operating system. That's how early computer viruses worked, is that they would try to deliberately overwrite the bounds of their program and see if they could get their code to be executed by, see if they could get illegal code to be executed by the operating system. Most operating systems today have protection against that, and they will just crash your program. They will just kill your program if it tries to overflow. Okay. Once you have an array, assuming you've been good and made a nice little capacity variable that indicates, a nice constant variable that indicates how big your array is, it's very easy to iterate through the entire array with a for loop. And now you begin to see why the for loop is set up the way it is, and particularly why, if you create a for loop in Xcode or Visual Studio, it will automatically populate the values with starting at I equals 0, going to I less than length or size or something like that. That's because those are the appropriate values to iterate through an array. You want to start at I equals 0 because that's the first index, and you want I to be less than, note this is not less than or equal to, capacity. That makes sure that you never reach that point at which you're overwriting your array's memory or reading from values that you don't have, that are not part of that array anymore. And then all you have to do is see out values at I, and you've written out, that loop will write out all the values in your array. Okay, so that is the type of for loop we will be using most of the time in this class, because we will not always want to visit the entire array. If your array is exactly the right size and you want to visit every value in the array, there is a special for loop for that. Sometimes called the for each loop or the ranged for loop. This will take each value in values and put it in the loop variable. I'm calling it value. It's often nice to give it a name that's related to the array. It'll take each value from values, put it in value one at a time, and then run through the loop once for each value. Okay. If you want to change the values in the array, you have to create the variable by reference. You have to put a little ampersand there, like passing a reference to a function. And then that will allow you to, say, add 10 to every value in the array. Okay. Little random tip here: use arrays only for sequences of related values. This should be a list of values that all have the same meaning. For example, scores on a test, or scores on your golf game, or whatever. Nothing prevents you from using an array, say personal data, and then I define a constant called age index, and I store my age there, and I store a ID index, and I store some identification number, and then I store shoe index, and I store my shoe size there. That's a really silly array. No professional programmer would take you seriously if they saw you making an array like that. It's generally considered bad style. In the next chapter, after our midterm, we'll learn how to use a struct to hold data that has various meanings to it. Okay, and that would be a much more appropriate thing to do with that set of data. Okay. Now, the reason we're not going to use the ranged for loop all that much in the rest of this class is that we often don't want to fill the array completely. For example, if we have a program that, as I mentioned before, is trying to keep track of your quiz grades and give you your quiz average in your class, it's fairly easy to get a number of quiz grades that you're not going to go above. So say you get a quiz grade every week and it's a 15-week class, you could define capacity to be 15. Maybe your professor gives you a pop quiz once in a while though, so maybe you'd want to go higher and set it at 20. In computers that have as much memory as most computers today do, it's pretty safe to make your capacity rather large. So we could make the capacity for our grade tracking program 100 and know that we're never going to get anywhere near 100 grades. If we do that though, we need to use a second variable called a companion variable that holds the current size of the array, the number of elements in the array that we're currently using. So say we add 4 elements to the array, we would set current size equals 4 to let ourselves know, to help us keep track of the fact that there are now 4 used spots in our array. So this is a way, I guess, of making an array somewhat like a vector, in that you can make it bigger than you need to use, and then you fill up only the amount that you're currently using. This is a loop that fills an array with user input. This is somewhat better than the version that's offered in your textbook because it says while current size is less than capacity and CN gives you valid input, then you will add a variable. That way we don't, the version in your textbook allows you to keep taking input even after you've reached the capacity of your array, which is sort of a silly thing for your program to do. But basically, each time through the input loop, you place the input into your array at the current size variable, which is now size -1, and then you plus the current size so that it now is equal to the number of items in your array again. How would you print the elements in a partially filled array? Well, we use the same for loop we did before, but instead of putting capacity here, we put current size. We say I is less than, again, make sure it's less than and not less than or equal to. I is less than current size, and this would print all the values that we're actually using in the array. Okay. Now, that's a good 30-minute lecture there for you. Probably time to pause this video and go try writing an array of your own. I've given you a practice problem on the Blackboard site that has you write an array to read your grades into to calculate an average and standard deviation. Okay. There are several common array algorithms. Some of these will look very familiar to you because they are just modified versions of the common input algorithms we learned in our loop chapter. Okay. One that's new is filling an array. If you want to fill an array with zeros, you just create a for loop that goes up to the given size and stores 0 in each value in the array. What if you want something more interesting, like all the perfect squares up to a given size? You create a for loop that goes up to size, and at each run through the loop, you're going to store I squared in squares at I. So squares at 0 would hold 0, squares at 1 would hold 1, squares at 2 would hold 4, and so forth and so on. Consider two arrays, squares, which holds the first 5 perfect squares, and lucky numbers, which is supposed to hold, say, maybe your 5 lottery numbers or something. What if we want to copy the values from squares into lucky numbers? It would seem easy to put lucky numbers equals squares, but this would be wrong. You cannot assign an array this way. The compiler will give you a syntax error. What you have to do is loop through the entire array, one element at a time, and assign the value from squares over to lucky numbers, one element at a time. You've already seen the algorithm for computing sum and average of a set of data that you're reading in from the keyboard. This is the same algorithm, except you're using a for loop to go through an array instead, to read your values in from an array. Similarly, we've seen how to find the maximum and the minimum. Instead of using input here, we use values at I, and we're going to run a for loop through the entire size of the array, or at least the current size of the array, the amount that we're using. For a minimum, you do exactly the same thing, but you reverse the comparison operator. One thing that's a little bit different than anything we've done so far is that when we want to print the elements of a array or vector, you may want to separate them with commas or vertical lines. One common way is to actually put a square bracket at the beginning, write each number with a vertical line, and then put a square bracket at the end, and that sort of makes it look like it's an array. The point is there are 5 elements, but there are only 1, 2, 3, 4 vertical lines, so there are fewer separators than there are numbers. To print 5 elements, you need 4 separators, so what we do is we only print the separator if I is greater than 0. Okay, so we don't print the separator before the first element. We do print it before the next one, and before the next one, and before the next one, and before the next one. And then before we enter the for loop, we can see out this first square bracket. And after we exit the for loop, we can print out this last square bracket. Okay. You could also, if you were doing a list of names and you wanted them separated by commas, you just replace the vertical bar with a comma, and maybe you put a period at the end after you've written all your values out. We want to find the position of a certain value. We can define a target here. Target equals 100. If the value at position equals target, we set found to be true, and that will exit us out of the loop. We also exit the loop if position is ever not less than size. Okay, if we run out of room in the array. Okay. In that case, position would return the same as size, and we'd know that there is no such value in the array, so we'd know that we failed to find the value. Removing an element is simple. If it's an unordered list, you just take the last element and you copy it over the element you're trying to remove, and then you minus the current size. If the order of the elements matters, you have to write a whole little for loop that goes from position +1 to current size and moves everything back one value, one spot in the array, and that's shown by this little diagram here. If we want to insert an element, all we have to do is go to current size, which is an unoccupied element at this point, store new element here, and then current size ++, the same thing we did when we were reading new values into the array from keyboard input. Again, if the order matters, we now have to copy everything forward a value in our list, which looks like this code here. We go from current size -1 to the current, the position we're trying to insert to, and we that's an oh, okay, we've just incremented current size. Okay. Suppose we need to swap 2 values. It's tempting to say values at I equals values at j equals values at I. But as soon as we do this statement, we've overwritten values at I, and values at I, we've lost whatever value was there before. So what we have to do instead is create a temp variable. We take values at I and we store it in temp. We take values at j and put it in I, and then we take the temporary value from temp and put it back in j, and that has successfully swapped the elements. Reading input, If we know exactly how many inputs the user is going to type, all we have to do is define that the array has exactly that number of inputs, and then we do a for loop that counts up to that number of inputs. However, rarely do we know exactly how many inputs we're going to have to start with, so we usually use this version where we keep both a capacity and a current size, and while current size is less than capacity and not or cn gives us valid input, then we store the input in values at current size and then plus our current size. Okay, here's a complete program that reads values until we hit capacity or the user hits Q to quit, and then it finds the largest value, and then it prints every element. If it's the largest value, it adds an output flag saying largest value. Okay. Sorting is a big deal in computer science. A lot of the algorithms that you'll study in algorithms class are sorting algorithms. Because sorting is such a big deal, there is a sort function that's actually built into the C++ library. There's a special library for mostly array and vector related algorithms called algorithm. And if you pound include algorithm, then you can just call the sort function from that. You pass it the name of the array and then the name of the array plus the current size of the array. It's a strange syntax, but it's how this particular sort function works. Okay. If you want to study sorting algorithms, there are a number of them out there, ranging from the spectacularly inefficient bubble sort to the relatively efficient quick sort. This is a somewhere in the middle algorithm where we read through the entire array once to find the minimum, swap the minimum into the sorted area, then read through the array starting after that one sorted value. We read through the entire array again, swap the value in, and so we end up reading through the array n times. We do n reads n times, so it's an order of n squared algorithm, which is not terribly efficient, but it works. Okay. One advantage of sorting is that we can then do something called a binary search. Okay, where we take the lowest and the highest number that we haven't searched yet, we average those together to get a midpoint, and we check whether that value is the searched value. If it is, great, we're done. If not, we check if it's less than the searched value, in which case this is a sorted list, so we know we have to look in the area in the values that are greater than that, so our new low value becomes position +1. If values is greater than searched value, then we know it has to be on the left side, position -1. Okay, finally, there are some more functions from the algorithm header that you should know. Copy will copy an entire array into array 2. Swap will just make that swapping of 2 items easier on you. Fill will fill an entire array up to a given size with value. So if you want to fill an array with zeros or -1s or any other sentinel value, you can do that. Min will check exactly 2 values and find the minimum of them. The one you're really interested in for an array is min element, which will look at an entire array and return the smallest element in the array. And there are 2 similar values for max and max element. All right, take a deep breath. Finally, we're going to talk about arrays and functions. Okay. Recall that when we work with unfilled arrays, we use a companion variable. The same concept applies when using arrays as function parameters. C++ makes some attempt to keep track of the size of your array in the function where it was defined, but once you pass it as a parameter into a function, C++ loses all track of how big that array was, and so you pass it with square brackets with nothing in between, and then you pass the size of the array, or at least the amount of the size of the array that you want the function to work with, as a second parameter. And then inside that array, the function can use your size that you passed as the size of the array and iterate over that whole size to, say in this case, sum up all the data in the array. You can pass the total number of scores to the array, and you'll get the sum of the entire array. You can also pass a smaller number, and you'll get the sum of just the first 5 numbers in your array. Nothing wrong with that. Note that arrays, because of the peculiarity of how they're defined as a reference to a memory location, are always passed by reference. Never use an ampersand with an array parameter. That's an error, but you can imagine that there's just sort of an automatic ampersand there, an automatic reference parameter. So if I pass in values and I try to multiply each value by factor, it's actually going to change the value in the original array that was passed to this as a parameter. Okay, you can pass an array into a function. You cannot return an array, but the function can modify the input array. Okay, if you want to copy from one array to another, you have to include both arrays in the parentheses. If you want to read inputs into an array, that's totally possible because, again, this is passed by reference. So this assignment actually stores the input in the original array that was passed to the function. When you call the function, you do not put any square brackets after the array name. You just put a comma and any other inputs, any other arguments. You can also pass, say, the size of the array as a reference parameter so that as you're adding to the array, you can increase the size and the calling function will know what that size was. Okay. The following program is going to use the read inputs, multiply, and print functions. Okay. Read inputs is going to enter values until you hit Q to quit. Okay. Then multiply is going to multiply everything by a factor. Print is just going to print them all out. Again, if I is greater than 0, we're going to print a comma to separate them. Okay, and then main just calls read inputs, then multiplies them all by 2, then prints them out. Okay, when a function doesn't modify an array parameter, good style is you can add the const reserved word like this, const double values. It's not actually going to keep your program from changing that, but the compiler will issue a warning if it detects that your function might change the original array. Okay, that concludes our section on common array algorithms and passing arrays to functions, which gets you ready for array practice 2, which is my second assignment for you. I believe this one has you writing a function to print your grades after you have read them in and sorted them. Okay, so you'll have to use that sort function. All right. Take a break, write some programs, then come back to watch Array Chapter 6, Part 2. Thank you.